Hello, welcome to this presentation about dynamic mechanical thermal analysis for polymer degradation evaluation. We will start first defining thermal analysis as a set of experimental techniques by which a physical or chemical property of a material is measured as a function of temperature, as established by the International Confederation for Thermal Analysis and Calorimetry. Particularly, dynamic mechanical thermal analysis is defined by the ICTAC as a technique that measures the mechanical module of a given material as a function of temperature and time or frequency. The response of the polymeric material to a mechanical disturbance gives information about its structure. First, linear, elastic, and viscous behaviors must be distinguished. In elastic materials, stress is proportional to strain. The proportionality constant is named modulus, which establishes a ratio between stress and strain. Several modulus are defined depending on the type of stress applied. Regarding viscous behavior, the relationship between the stress and strain is governed by Newton's law. In this case, the proportionality constant is called viscosity. Viscoelastic materials show an intermediate behavior between elastic and viscous performance. When a viscoelastic solid is subjected to a constant tension, the deformation produced is not constant but slightly increases with time due to a molecular reorganization induced by the applied tension. When the tension disappears, the molecules slowly recover their initial spatial order and simultaneously the deformation turns zero. Due to their particular molecular structure, polymers possess a high number of atoms, which allows infinite possibilities of atomic distribution. In polymers, the stress-strain adaptation is not therefore instantaneous. Instead, they are a function of time and temperature and are known as relaxation phenomena, with particular relaxation or adaptation times. The mechanical response of viscoelastic materials to mechanical disturbances has traditionally been modeled in terms of elastic using a spring element and the viscous component using a dashpot. The Maxwell model consists of a spring in series with a dashpot, while the Boyle's model consists of a spring and dashpot in parallel. The relaxation time for both models consists of a ratio between the viscosity and the corresponding modulus. In viscoelastic materials, the mechanical modulus can vary depending on the way the disturbance is applied to the sample. For instance, we can distinguish between shear, extension, or compression. Additionally, in linear viscoelasticity, these parameters are correlated. All the previous slides have assumed that only one relaxation process can occur in a given polymer. However, viscoelastic materials are far more complex and have many relaxation processes. Therefore, models describing real viscoelastic solids are built as the sum of individual components for explaining all the relaxation processes in a given material. The MTA performs a dynamic experiment where a stress is applied to a sample. The response of the sample is not direct, but it lags a certain degree. Thus, the modulus are of complex nature. The most important notion is that the complex modulus, whether it's Young or shear modulus, can be written as the sum of a real and imaginary part. Subsequently, the real part is associated with the amount of energy that is stored, whereas the imaginary part represents the amount of energy that is lost in the form of heat. In dynamic experiments, the variation of the curves can be understood as follows. If the storage modulus increases progressively, it can be ascribed to a rigid or rubbery solid according to the value range. If the loss modulus presents a maximum For this point, perturbation frequency coincides with the relaxation time of the material. If the loss modulus is 0, the solid is deformed in a reversible elastic way. Finally, for loss modulus larger than 0, the deformation of the solid is not perfectly reversible elastic. The aim of the MTA analysis is to understand the molecular transitions in which the structure of the polymer undergoes physical changes. At low temperatures, the structure is in a glass-like state, and therefore only lateral groups motions are registered. At higher temperatures, above Pg, the polymer undergoes the glass transition, and consequently there is a change from the glass-like structure to a rubbery state in which cooperative movements are allowed, and therefore the molecular processes register the motion of the main chain. A DMTA equipment consists of three main elements: a dynamic mechanical head, a temperature programmer, and an analyzer, which will be explained. The dynamic mechanical header allows deflection of the sample with harmonic load that is applied in its midpoint, as shown in the figures for two different DMTA analyzers. It's possible to select different frequencies that cover a range from 0.001 Hz to 100 Hz. Usually, the maximum force that can be applied is 4 Newton, and the minimum displacement that can be analyzed is 10 micrometers. The temperature programmer allows the measurements with different heating rates, from 0.1 degrees per minute to 20 degrees per minute, using a temperature range from minus 150 to 300 degrees. The MTA allows to determine several mechanical modulus, and for that reason there are different types of clamps. It's very important to highlight that every clamp has its own geometrical factor, which is of paramount importance to determine the complex modulus appropriately. The geometrical factor is strictly correlated to the sample geometry, the vibrator, and the used clamps and frames. A DMTA experiment usually pursues obtaining the relaxation function, the activation energy for all the molecular processes, and the determination of the amount of free volume in amorphous polymers. In general, in order to characterize the molecular relaxation, a fitting model is used. In this slide, an example with the Foss-Kirwood model is shown, in which the raw data was fitted to a given model. Thereafter, as most of the polymers have multiple relaxation processes, the curve must be deconvoluted in order to determine each individual contribution. Finally, it's important to highlight that the determination of relaxation processes at the entire temperature range allow to determine their activation energy. For that purpose, the Arrhenius model is usually employed for relaxation showing a linear dependence between the relaxation times and the temperature. On the contrary, if a nonlinear dependence is found, the Vogel-Fulcher-Taman-Hess model is employed. The latter allows us to study the molecular processes in terms of fragility index or the free volume. At this point, we reach the end of this presentation, and we would like to thank you for attending, and we hope to see you in the other videos of this series. Thank you.